Lesson deals with supplemental problem 414. You can find this problem in the ECE302 ebook in the Chapter 4 Supplemental Problems, starting on page 31. Given the following CMOS logic circuit, can you draw a resistor equivalent circuit and create two tables like we found in Chapter 4, page 44, and solve for V out? So here I've got 6 MOSFETs interconnected. I've got 3 inputs, V sub A, V sub B, and V sub C. And these are all the possible combinations of 0 and 5 volts. The top 3 transistors are P-channel MOSFETs and the bottom are N-channel. And you can see that the P-channel MOSFETs has their bulk material hooked up to the most positive potential in the circuit, and the N-channel devices have their bulks hooked up to the most negative potential in the circuit. If you recall in our Chapter 4 notes, we used a technique where if we had a small resistance multiplied by a small current, we treat it as 0 volts. Or if we had a large resistance multiplying a small current, it could be any possible value, but because it's between a 0 and 5 volt power supply, it does limit the range of numerical values. If our transistors are operating either in ohmic or cutoff, they look like a resistance between the source and drain or between the drain and source. Let's draw an equivalent resistive circuit for this, assuming that that's true. Between these two nodes, I've got a resistance, I'll call it R sub SD1. Between here and here, R sub SD2. Between here and here, R sub SD3, R sub DS4, R sub DS5, and R sub DS6. So I basically have a voltage divider, and we'll get the value of voltage here based on the values of these resistances. To make things simpler, let's assume that the threshold voltage is 1 volt. Next, I'm going to assume that the current here is small. The reason I'm doing that is that when a transistor has a source-to-gate voltage or a gate-to-source voltage greater than threshold, that transistor could be in the ohmic region or the current saturation region. But if the current going through it is very small, then we're going to be in the ohmic region. That's a trick we used in the Chapter 4 notes. We're going to assume this. We're going to also show that it's true at the end once we get our final guesses in. In the table below, the first row is having all zeros as inputs. This is 0, this is 0, this is 0, 0, 0, and 0. Let's figure out the source to gate and the gate to source voltages on the outer transistors because that's the easiest. So this is 0 volts. That's going to mean that we're in cutoff. It makes this resistance a large value, and let's just use a number to make things easier. I'll call this 1 gigaohm. And likewise, this is 0 volts. That would make this 1 gigaohm. The voltage from here to here is going to be 5 minus 0. It's going to be 5 volts. Let's assume that we're in ohmic, and that'll make this a low resistance. Suppose we just use 1 ohm as a small value. Likewise, the source to gate voltage here is 5 volts. That's going to make this a low resistance, say of 1 ohm. And then the voltage between here and here, let's see if we can figure it out. Now, if this is 1 ohm, and I've got a small current going through it, then this voltage here is about 5 volts. This is about 5 volts. That's going to make the source to gate voltage equal to 5, and that would make this also a low resistance. Then one last one over here. If this is a high resistance, then I don't know the voltage across here. I know it's between 0 and 5. If I take this node voltage minus this one, I've got 0 minus something between 0 and 5. The voltage across here is going to either be negative or 0. It's going to be less than or equal to 0. That means that we're in cutoff over here. I would make this a high resistance also. I've got a voltage divider. So V out is equal to 5 volts. I've got these two in parallel to be a half a gigaohm, 1.5 gigaohms over 1.5 gigaohms. This is going to be equal to 2 in parallel with 1 plus 2 in parallel with 1, which is very small. That's going to make this expression about 5 volts. Lastly, we need to check that this current is small that's coming in here. We've got 5 volts divided by the total resistance. What I've got over here is a half a gigohm in series with a gigohm. It's 1.5 gigohms. This is a small value of 2 in parallel with 1. Basically, I have 5 volts divided by something in gigaohms, so I'm going to get nanoamps of current. but checks that we have a small current coming in, and our assumptions that our transistors were in the ohmic region and not in current saturation was correct. Let me erase this so we can do the next case. Next line in the table below is 0, 0, 5. This is 0, this is 0, and this is 5. And this is 5, and this is 0, and this is 0. Let's do the outer transistors. Those are the easiest to calculate. So gate to source voltage here is 0. That's going to make this a very high resistance. Again, let's just say it's 1 gigaohm. Likewise, the voltage between here and here is 0. That would make this 1 gigaohm. The voltage between here and here is going to be 5 volts minus 5 volts. This is also 0. That's going to make this 1 gigaohm. And the voltage between here and here is going to be 5 volts minus 0. It's 5. It's going to be a low resistance because we're going to assume that we're in ohmic if the current is small. And likewise over here, if this is a low resistance, then the drop across here will be very small. And this node voltage is about 5 volts. This would be 5 volts minus 0, about 5 volts. It would be something greater than threshold, but because the current is assumed to be small, we're in the ohmic region. Find this one. Because we're in cutoff, you don't know the value of the resistance. Something is very large. This is 5 volts, and then this voltage here can be anywhere between 0 and 5 volts. You don't know the voltage across here. This becomes a don't know. Could be a high resistance, could be a low resistance. Let's check to see if we have a small current. Because I have these two in parallel, I have a very high resistance in series with all of this. No matter what this is, it's going to be a small current. I've got 5 volts divided by something in gigaohms, so we're looking at nanoamps. Assumption checks. Let's now go and calculate V out with this don't know. I've got 5 volts multiplying this divider. I've got a half a gigohm plus don't know. So 0.5 gig plus something else divided by the same thing. Here I've got 2 ohms in parallel with a gigaohm, which is about 2 ohms. That's going to give me a large number divided by an equally large number, so about 5 volts. Let me erase these so I can do the next case. The next row in this table below is to have 0, 5, 0, 0, 5, 0, 0 here, 0 here, and 5 over here. Take the outer transistors and calculate their gate to source or source to gate voltage. It's going to be 0. Since we're less than threshold, we would be in cutoffs. Big resistance here, say 1 gigaohm. This is between 5 volts and 0. This is 5 volts. This is going to be either an ohmic or current saturation, but if the current is small, it would be an ohmic. It would be something small, say 1 ohm. The voltage across here is going to be 5 volts minus 0. This is 5 volts. It would likewise be an ohmic. Between here and here, I have 5 volts again, 5 minus 0. So that would make this a low resistance. The low resistance here, I've got a small current, and this would be sitting at about 5 volts. The voltage between here and here would be 0. Put this in cutoff, or 1 gigaohm. With this being 1 ohm, parallel with this, just going to make it still 1 ohm, this voltage is going to be very close to 0. The voltage across here is going to be 0 minus a number very close to 0, about 0 volts. Put this in cutoff, and again give me 1 gigaohm. Let's check if our current is small. I've got 1 gigaohm in series with this, in series with this. The current that's flowing is 5 divided by 1 gigaohm plus 2 other numbers. It's going to be a small current, something in nanoamps. Let's solve for V out. 5 volts, my voltage divider. I've got 1 gigaohm in parallel with 1 ohm, which is about 1 ohm. In series with a gigaohm is about a gigaohm, over a gigaohm. Plus, I've got 1 gigaohm in series with 1, about 1 gigaohm, but that's in parallel with 1. It's going to be about 1 ohm. That's going to give me about 5 volts. Let me erase this so we can do the next case. The next line in the table below is 055. So 0, 5, 5, 5, 0, and 5. Gate to source voltage 0, being cutoffs, big resistance, say 1 gigaohm. The gate to source is 5 volts, would be an ohmic if this current is small. The voltage between here and here is 5 minus 5, or 0. That would make this a large resistance. The voltage between here and here is 5 minus 0, or 5. That would make this a low resistance. And then the voltage between here and here, calculate. If this is a small resistance and a small current, and the drop across here is approximately 0, this is sitting at about 5 volts. 5 minus 5 is 0. That would make this 1 gigaohm. And then with this being a low resistance here, that makes this node voltage a very small voltage, say 0. Voltage across here is going to be 5 minus something close to 0, so 5 volts. That's going to put this in the ohmic region, roughly 1 ohm. Do we have a small current? Well, I have a gigaohm in parallel with roughly a gigaohm. In series with this, divided into 5 is going to be something in nanoamps. Yes, we have a small current. Solve for V out. It's going to be equal to 5 volts times 1 in parallel with 1 gigaohm is roughly 1 ohm, plus 1 ohm is roughly 2 ohms. And likewise in the denominator, we've got 1 gigaohm in parallel with 1 gigaohm, about a half a gigaohm. We've got 10 divided by roughly half a gigaohm, something that's very close to 0, something in nanovolts. Let me erase this so we can do the next case. The next row in the table below is to have 5, 0, and 0. So I would make this 5, 0, and 0. Gate to source voltage here is going to be 5 volts. That means this is either an ohmic or current saturation, but if we assume a small current, that would put us in ohmic, 1 ohm. This has got 0 volts, being cutoff, 1 gigaohm. Voltage between here and here is 5 volts minus 0, 5 volts. That would make this 1 ohm. The voltage between here and here is 5 minus 5, so 0. That's going to make this 1 gigaohm. Now what about this voltage? Now if I have a small current going through here, I can't figure out this voltage, but this is in parallel with everything, so that small current is also going down this other path. That makes this node voltage here about 5 volts. That makes this about 5 volts also. This minus this would be 5 volts. That would make this a low resistance. Likewise over here, having a low resistance back to ground, this is going to be sitting at something close to 0 volts. 0 minus 0 is 0, 1 gigaohm. Do I have a small current? Well, I have 1 gigaohm in series with this, in series with this. Something when I divide that into 5 volts in nanoamps, so I have a small current. Let's solve for V out. Just a voltage divider. 5 volts. I've got 1 ohm in parallel with 1 gigaohm. That's about 1 ohm. In series with 1 gigaohm is about 1 gigaohm. And then I've got 1 gigaohm here. And then I've got 1 gigaohm in series with 1, roughly 1 gigaohm, but that's in parallel with 1, it's about 1 ohm. What I've got is 5 volts times a big number divided by about the same big number. It's about 5 volts. Let me erase this so I can do the next case. The next row in the table below is 5, 0, 5. So 5, 0, 5, 5, 0, 5. Gate to source voltage is 5 volts. Would guess that this is an ohmic with maybe a 1 ohm resistance. This is between 0 volts and 0. So this is 0 volts. That makes this a big resistance if it's in cutoff. Between here and here, I've got 5 volts minus 5 volts. I've got 0. That makes this a big resistance. Between here and here, I've got 5 volts minus 5 volts. That's 0. That makes this a big resistance. Now having a 1 ohm back to ground here, this node voltage is about 0 volts. The gate to source voltage here would be 5 minus something close to 0, so this would be 5 volts. Also be 1 ohm. What about this voltage? Well, I've got a high resistance. No, the drop across here. This node voltage is unknown, but it's something between 0 and 5. If I calculate the voltage between here and here, I've got a number between 0 and 5 minus 0. This could be greater than threshold or less than threshold. I just don't know. Call this a don't know. Let's see if that impacts our answer. V out is equal to following. Let's quickly check that we also have a high resistance between the power supply and ground before we do this. I've got 1 gig ohm in parallel with 1 gig ohm plus something that could be big or small. This is at least a half a gig ohm in series with something here that's pretty small, but dividing that into 5 volts, we've got nanoamps. Yes, that checks. We do have a small current. The voltage divider then is 5 volts. 1 in parallel with 1 gig ohm is roughly 1 ohm. In series with 1 would give me about 2 ohms divided by 2, plus I have 1 gig ohm in parallel with 1 gig ohm plus something. So I've got 1 gig ohm in parallel with 1 gig ohm plus something else. This is at least a half a gig ohm or so. At 5 times 2 divided by a huge number, so this is very close to something around 0 volts. Let me erase this so we can do the next case. Next row on the table below is 550, 550, 550. Gate to source voltage is 5. Would guess that this is a low resistance. This one's also 5. Guess that this is a low resistance. This is going to be 5 minus 0, 5 volts. Likewise, I'd assume that I'm in ohmic. Between here and here, I've got 5 minus 5, which is 0. So put me in cutoff. And I got to try to figure out this node voltage. I do have a low resistance back to ground, just sitting at about 0 volts. Voltage between here and here is going to be 0 minus something close to 0, about 0 volts, to make this a big resistance. I do have a resistor between here and here of 1 ohm. So there's a small current going down here and here. This is sitting at about 5 volts. It must be sitting at about 5 volts. The source to gate voltage is going to be 0, which is going to make this a large resistance, a gig ohm. Double check that we do have a high resistance total. I've got 1 gig ohm in series with a half an ohm, in series with something up here. So that's something in gig ohms. Divided into 5 would be in nanoamps. That checks. Let's solve for V out. It's going to be 5 volts times half an ohm in series with 1 gig ohm, hopefully 1 gig ohm, over that 1 gig ohm, plus I've got 2 gig ohms in parallel with 1, which is about 1 ohm. That's going to be roughly a big number divided by the same big number, about 5 volts. Erase this so I can do the last case. Last case in the table below is 5, 5, and 5. 5, 5, 5, 5, and 5 volts. Got a gate to source voltage of 5 volts. Would guess that this is an ohmic, maybe 1 ohm. Likewise, this is 5 volts. Guess that that's an ohmic, 1 ohm. The voltage across here and here is 5 minus 5 or 0. Guess that this is in cutoff. Voltage between here and here is 5 minus 5, which is 0. So that would also be in cutoff. Now having 1 ohm here, that's going to make this voltage approximately 0. So it's going to make this 5 volts minus 0, 5 volts. And again, I guess that that's in the ohmic region. I've got about 0 volts here, but I don't know what this voltage is. I've got a big resistance and a big resistance. Could have any drop across here between 0 and 5. This is unknown. The value of the source to gate voltage is going to be some number between 0 and 5 minus 5. That's going to be less than or equal to 0. So I'm going to put this in cutoff and give me likewise a gig ohm. Do I have a small current? I've got a low resistance here, but this parallel combination is something in the low gig ohm range. And that's divided into 5 volt. Get nanoamps, so that checks. V out is equal to 5 volts times half an ohm in series with 1, so that's 1.5 ohms. And this top part of the circuit, we have 2 gigaohms in parallel with 1 gigaohm. So 2 gigs in parallel with 1 gig, and that's a little bit less than 1 gigaohm. We have a small numerator and a large denominator. This is approximately 0 volts. What's shown below, results we just did in finding the source to gate and the gate to source voltages and all the combinations that we found for the 8 possible inputs output voltages and high-low resistances. We found for these cases the output was 555055050. You can make any logic function out of NAND gates and NOR gates, but you can build a function with far fewer transistors by doing what we just did, creating voltage dividers that would give you the expression that you want. If you've had a course in digital logic, you can actually take this table and figure out the Boolean expression. In this case, it's A or B and C complemented. And this is supplemental problem 414.